Have you ever wondered how big the Earth really is? In this video, Fecore will guide you through a thought process to show how a simple idea of a measurement developed into a discovery that shakes the foundation of our current scientific understanding based on the WGS-84 map system, which is the accepted model for Earth's shape and surface. You may want to brace yourself. The curvature. Earth is said to be a sphere with a circumference of 25,000 miles or 40,000 kilometers. Therefore, it has to have a curvature of about 8 inches per mile squared. Can we observe or verify this? We are taught about the ancient observations like a sailing boat going over the horizon and the measurements of Eratosthenes. They are all falsified by our current observations and better understanding of the optical effects of the atmosphere. But how can we really measure the curvature of the Earth in the 21st century? Fecore has established the Terrestrial Laser Targeting Method, or TLT method for short, to measure the geopotential surface of the Earth. Geopotential means the shape that the ocean surface takes under the influence of gravity. With the TLT method, you can accurately verify or falsify the curved surface defined by the WGS-84 geoid model on large bodies of water. The origin of Fecore. Before Fecore was formed, 3 independent researchers became aware of the need to perform accurate observations regarding the Earth and other celestial bodies. Steve, Zach, and Mike had seen videos of each other's research. They began working together to publish their research on the internet. In time, they added other people to their informal research group. In October of 2017, Mike suggested they form a non-profit organization so they could expand their research efforts by inviting people to donate time and financial resources of their choosing to advance the independent research. In December of 2017, Fecore was formed according to U.S. regulations for a 501c3 organization. Fecore stands for Field Engineers Corps. Fecore is an independent research group dedicated to discovering the facts about the Earth by observation and utilizing the scientific method. Sandor is an inventor from Hungary who joined Fecore from the beginning. Sandor had also been considering how to verify that bodies of water conform with the WGS-84 geoid model. In 2016, he decided to test this by using a laser beam over the surface of water.
Zach and I decided to recreate an experiment similar to Stephen Hawking's experiment to prove that the surface of the water actually curves according to the curvature of the Earth. Hawking's target was 3 miles away, and it seemed to match the curvature of the WGS-84 geoid model. But his results looked strange to me because I could see the shore on the other side of Lake Balaton, which is a lot further away than his distance of 3 miles. So we decided to do a laser experiment with a few other friends. We chose to perform the first test over Lake Balaton, Hungary, about an hour drive southwest of Budapest. It's approximately 48 miles or 77 kilometers long, by an average of 4 to 6 miles or 7 to 10 kilometers wide. So it provides a long distance for a line-of-sight laser observation. Balaton also has many locations to carry out such an experiment.
So why a laser and why over water?
A laser is a special type of light source. It's coherent and collimated, which means that all the light is travelling in the same direction and is extremely concentrated into a narrow beam. This makes a laser visible for many miles and is very useful for verifying a point-to-point measurement. Water appears to provide a flat surface with no obstructions over long distances, so it's an obvious choice to use this location for the measurement. Although TLT measurements can be performed on any terrain surface, a large body of water is representative of the geopotential surface. According to mainstream science, the water's surface is primarily shaped by the Earth's gravitational field.
The experiment setup was designed to answer this question. Could the source of a laser beam be seen and recorded from a distance that should be hidden by curvature according to the WGS-84 mathematical construct? If not, is there anything blocking our sight, like weather conditions? If yes, what factors must be accounted for? To verify or falsify a possible theory, you must account for the other possibilities. Is a light ray perfectly straight? Here you must investigate the refraction of light, how much the laser beam deviates from an absolutely straight line and in what direction. Light propagates in a straight path and only refracts when the path of the beam crosses a medium with different refractive qualities. Fecore used a ray of the collimated laser beam to verify the curvature of the surface by considering the refraction data. The refraction calculation for each TLT measurement is shown in the Fecore document that is presented in this video.
Factors in measuring the geoid model. Let's take a minute to demonstrate the factors in measuring the geoid model. How much should be hidden from our sight by the calculated convexity of a body of water?
The geode model, or WGS-84 mathematical construct, states the Earth is an oblate spheroid 24,900 miles or 40,075 kilometers in circumference at the equator, and 24,860 miles or 40,008 kilometers circumference over the poles. If this is accurate, then given these parameters, the surface of the body of water must have an average convexity roughly equal to 8 inches per mile squared in all directions. This means in 1 mile, the surface on average will be 8 inches lower compared to the starting point. But in 2 miles, the convex surface must be calculated as 8 inches times 2 miles squared, which is 8 times 4, or 32 inches. At 3 miles away, there must be a 72-inch drop, and in 10 miles, a drop of 66.6 feet, or 800 inches. In metric units, a 5-kilometer distance should create a 2-meter drop, and a 10-kilometer distance, a 7.84 meter drop. This calculation would give a result of 1,525 feet, or 465 meters, on the total distance of 48 miles, which is 77 kilometers, over Lake Balaton.
The polar and equatorial circumference differential is relatively insignificant to factor in, but Fecore did calculate the ellipsoid correction for each measurement. This correction value in the magnitude of 1/25 of an inch, or 1 millimeter, is well below the margin of error for the TLT measurement method. The WGS-84 geoid is not a perfect ellipsoid geopotential surface, and it may have local anomalies. Deviation from the perfect ellipsoid surface is called geoid undulation. The WGS-84 geoid undulation map shows these correction values, so this data can be compared with laser and target positions. When we stand by a lake or the ocean in the curved surface model, the height of our eye level above the surface of the water determines just how far we can see before the convex shape of the water would begin hiding objects from our view. The point where our line of sight would be blocked by the water is called the horizon, so the distance to the horizon would be determined by the height of our eyes or camera above the surface of the water.
Many people argue about leveling the laser above water. Some people think it is an easy thing to do, like leveling a frame on a wall. And most people think that using the spirit level is more than enough. But the important question is leveling the laser even important in such an experiment?
You know, Zach's going to cry about the spirit level, right? Yeah, Zach, we know you don't like spirit levels.
In geometry, there is no level in a line above a convex surface. Mathematically speaking, the laser can be parallel to the ground only if the ground is flat, but if the Earth is a globe, then no straight line can be parallel to its surface. With that being said, there is a way to make a straight line if you're drawing it by hand, but in reality, it's not an easy task because it's a very long line and using a spirit level will never give you an accurate results. Because the laser beam is many kilometers long and any small error or movement of the device will cause the beam to be drastically off the mark at the target location. But in our case, leveling the laser is not even needed. What we need to do is choose a target location that will be impossible for the laser to hit since it will be hidden behind the convex surface. Then we shoot the laser to the lowest point possible on the horizon line. In this case, the laser is actually pointing slightly downwards while we try to keep the laser tangent to the globe. We will then see if it is visible from the target location since it should be blocked behind the curvature of the Earth.
Looking at the horizon line, we always notice that ships or even cars become invisible from the bottom, as if there is something in the air that gives us that illusion. So what if this something affects the laser beam as well?
Placing the laser close to the water surface increases the problems with the refraction caused by what we call the non-uniform density transition zone, or the NUTS. It is a zone just above the water surface. It is ideal to place the laser at least 7 feet or 2 meters above the water surface to avoid this area of light disturbance. You also have to take into account that the laser beam diverges with distance from one side to the other, creating a very long cone. Because of this divergence, the bottom of the beam will eventually contact the water surface. In order to avoid this, a very collimated lens is needed. Collimation is a technique that converges the laser beam, enabling it to reach longer distances, but that doesn't mean that it will never diverge again. You have to study the distance you are measuring, the height of the laser, the divergence of the beam in that distance, the humidity, and the collimation, etc. So it's not as simple as many people think.
Sandor's tests before Fecore.
So, let's start it.
In the year prior to the formation of Fecore, Sandor performed 2 laser tests to measure the geoid. He hired a laser specialist to custom build a 3-watt green laser with a 0.08 millirad collimated beam. He and his assistants then met at Lake Balaton, Hungary. In June of 2016, they performed a pre-test to verify the method with the boat following the laser beam and taking height measurements along the surface of the water.
A notable event during the pre-test showed how easy it is for the observation team to lose sight of the laser, even though it's only a few meters right or left. When the team was about 3 kilometers away, they lost sight of the laser. When a large boat passed by, we could see the laser on the hull of the other boat still very close to them.
During a second attempt in August of 2016, measurements were made with different heights of the laser above the surface of the water. At one point during the test, the laser was at 1.64 feet, or 50 centimeters, above the lake surface and appeared to turn sharply upward and split into 2 beams. This was later found to be caused by the laser having a slight downward pitch, which forced the beam to collide with an air layer at such an angle above the water at 5,000 feet or 1,500 meters distance away, it reflected part of the beam upward. In the early morning hours of August 16th, Dave Murphy and Niku Bariku spotted the laser beam and recorded it from over 3.72 miles or 6 kilometers from the shore. This measurement indicated a non-convex surface, but Sandor wanted a more definitive measurement with ambient condition readings for any refraction arguments. The difficulties of aligning the laser parallel to the surface on the measurements pointed out the need to use a very accurate laser aiming device to provide precise targeting. The salad. Fecore decided to continue the curvature tests at Lake Balaton, but with a more ambitious goal of pointing the laser across a longer portion of the lake. This would attempt to measure the convexity of the lake over 41 miles or 67 kilometers. The previous tests by Sandor had been conducted in the summer and showed some refraction anomalies. Therefore, it was decided to perform the measurements in winter conditions over a frozen lake to minimize the optical density differences along the path of the laser beam. According to the plan, the observation team would keep contact with the laser position as they walked across the ice while taking laser height measurements at the previously planned positions. The first objective for the Balaton test was to design and build a laser aiming device which could make a 41-mile, 67-kilometer observation possible. Mike, Fecore's president, took the assignment. He designed and built a laser mount capable of extremely fine adjustments for both the tilt, which is the vertical motion, and for panning, the horizontal motion. The result was the Super Accurate Laser Aiming Device, or SALAD for short. The instrument had an accuracy of 54 millionths of a degree in the tilt angle and 34 millionths of a degree in its panning motion. This was accomplished with two high-tech stepper motors capable of making movements as small as 1/10,000th of a rotation. That is equal to 36 1,000th of a degree. This rotation movement was transferred to a bolt with fine threads 1.5 millimeters apart. That meant the rail where the laser was attached could be moved in steps of 15 100ths of a micron. That is less than 1/1000th the thickness of the thinnest human hair. Over 1,000 man-hours went into the design, build, and refinement of the SALAD. The materials alone cost over 20,000 euros or 23,000 US dollars. But because Fecore is a non-profit organization, those funds were received via donations. This was where the value of forming Fecore as a 501c3 entity became obvious, as corporations who donate materials or financial resources to a nonprofit organization benefit from the tax savings. The TLT method for measuring curvature.
Terrestrial laser targeting is designed to be a curvature surveying method over long distances. The idea is to prove a straight line on a surface between 2 points by shooting the laser to the target location and verifying the height of the beam at each side.
The targeting accuracy depends on the aiming device. Without proper targeting accuracy, this experiment is not viable. Fecore's SALAD was the key element in developing the TLT method. The required accuracy depends on the deliverable output. Accuracy refers to how closely a measurement or observation compares to a true or established value, since measurements and observations are subject to errors. The precision of the TLT measurement is expected to be within 1% of the volume compared to the target hidden height calculated on each measurement's distance to arrive at a definitive result. Before going into the presentation of each measurement, the integrity of the TLT method must be verified. This was accomplished by adjusting the laser and calculating the vertical change at the source with respect to the vertical change at the target location.
We're going to put the collimated laser on the mount with the mount in position and then try to locate that smaller beam and get some measurements today.
It was explained earlier how the WGS-84 mathematical construct is used to calculate the geospatial surface. Based on that model, the outcome of the experiment can be calculated. The lowest height where the laser is visible is measured and compared with the model's prediction. Terrestrial laser targeting is a definitive and repeatable method to verify or falsify the WGS-84 mathematical construct. Refraction is when light deviates from a straight path while passing through mediums of different optical density or refractive index. For example, air at standard conditions has a refractive index of 1.0003. Water has a refractive index of 1.333. Propane gas has a similar refractive index of 1.34. Optical density is not the same as physical density. Layers of the air are positioned by their physical density, not by their optical density. The light beam changes direction when crossing different optical density mediums, such as warmer or more humid air. This apparent bending of the light beam is always in the direction of higher optical density, which is defined by the refractive index of the medium. Refraction only takes place on the border between two different optical densities. No refraction occurs unless the path of the light crosses a boundary to another layer with a different refractive index. In nature, There are no other forces such as gravity or magnetic fields that cause light's path to refract up or down over 10 miles, or even 7,000 miles. If it did, then the appearance of the location of the sun in the sky would jump from one day to the next in the case of a solar storm or magnetic anomaly.
The incidence angle and the refraction calculations within our document are not vertical but horizontal. We do not shoot the laser at an angle through a horizontal medium. We shoot with a zero angle of incidence through a relatively homogeneous medium. That is why the laser is used well above the surface of the water to avoid the non-uniform density transition zone. Also, there is an argument of beam divergence. Beam divergence does not affect the TLT measurement. And talking about measurement, I would have to add, the measurement does not use the full beam, but instead only a ray of the laser that is coming directly from the source to the observer. And to conclude, the symmetrical white flash in the center of the optics indicates that we are observing the source of the beam in a direct line of sight.
Fecore performed 7 documented TLT measurements in 2018. 2 were at Lake Balaton in Hungary, and 5 were performed at Lake IJssel in the Netherlands. Based on the collected data, Fecore now has evidence that falsifies the WGS-84 mathematical construct. This has huge implications to our current understanding of Earth's geometric shape. Fecore laser measurements at Lake Balaton 2018. January 2018 pre-test. The original plan was to perform the test in January because Lake Balaton normally freezes solid that month, but in 2018 the weather did not cooperate. The January temperatures were too high for a solid freeze, so it was decided to reschedule for February in hopes the lake would be frozen.
On January 8, Sander and I went to the Lake Balaton for pre-test observations. We found that we could keep track of the laser by walking along the edge of the lake as the laser operator slowly panned the laser in just one direction. With this method, a frozen lake was not even necessary, but still preferable, of course.
Fecore spent hours late into the night to discover how the test could be carried out. The pre-test was done under harsh weather conditions of sub-freezing temperatures. Nevertheless, it was a very exciting experience, as observers were able to see the laser at an astounding distance of 21 kilometers with the naked eye. The moment was captured by Sandor's camera. It was a clear indication of the missing convexity of the water surface. The 1-month delay gave Mike more time to test the salad and to adjust its operation software.
Zach and I just finished the pre-test. We didn't take any measurements because the weather was not helpful, so we focused on checking the laser performance and the measurement positions. But while we were checking the positions planned for the measurement, the foggy weather started to clear out, and suddenly we could see the laser from 21 kilometers distance. We spotted the laser beam 1.5 meters above the lake surface, standing on the shore.
On February 21st, Fecore members from 10 countries gathered at Lake Balaton to perform the long-range terrestrial laser targeting experiment that was designed to verify the lake's convexity. The weather was cold, but unfortunately, the lake was still not frozen.
On the first day, we set up the laser position in a tent beside the lake in the garden of the hotel. The custom-built laser required a minimum air temperature of 10 degrees Celsius or 50 Fahrenheit for operation. The laser began to malfunction due to the outside temperature hovering around 3 degrees Celsius or 37 Fahrenheit. So a small electric heater was placed near the laser cooling fan intake. The warm air over the cold laser cracked the crystal in front of the laser diode, which caused the beam to be distorted and the focus malfunctioned. Fortunately, the laser specialist had other lasers with them and were able to swap out the laser on the salad so the team could proceed with the planned observations.
The weather continued to wreak havoc on the team and equipment. Besides being very cold, only 2 of the 7 nights were clear enough to see the laser from any observation point. The salad worked well to make very precise adjustments, but locating the beam by the observation team on the opposite shore at night was very difficult. Although the salad was able to pan and pitch in small enough increments, an hour was required to establish contact between the observation teams.
Yeah, if you can get back there, I would definitely recommend it because I think you're going to see something. Before we weren't sure what the problem was. We could have also been pitched down, but we also had possible waves we were hitting. Because if the waves were like 2 meters, that's about the height that we are. But now we don't have that problem, and we're also not bouncing off the water like we were before.
The targeting procedure at Lake Balaton was implemented by locating landmarks visible during the daytime and aiming the salad in the direction of where the observation team would go at night. To aid in the aiming, Fecore used a Nikon P900 and a Celestron Power Seeker 70 EQ telescope. However, even at night, this required the observer to be close to the beam to spot the laser.
One of the primary problems that we were also facing is that especially at nighttime, we have no idea where we're pointing at. We could manually or visually find the locations during the day, but we have to shoot the laser at night for us to see it. And as soon as it turns dark, you have no idea where you're shooting at.
After sunset and the initial leveling process of the salad, the beam was adjusted parallel to the water's surface. The observation team then spread out along the shore to find the laser beam while maintaining contact via phone. Measurement 1. On February 22, 2018, at 10:44 p.m.,
on the first day, we had a successful observation, but we became aware of it only after analyzing the recorded footage. My camera at the garden of the hotel recorded the handheld blue laser pointer used by the observation team as they were giving targeting signals from the opposite shore 12 kilometers away.
The blue laser pointer was 1.5 meters or 4.92 feet above the surface of the water. Karen's camera was 1.6 meters or 5.25 feet above the surface of the water at a distance of 12 kilometers or 7.46 miles. The 12-kilometer distance calculation based upon the WGS-84 model results in a target hidden height of 4.56 meters or 14.96 feet. The lake temperature was 2 degrees Celsius and the air temperature above the lake was 3 degrees Celsius. The ambient conditions showed the refractive indexes were about the same at the two sides of the lake where the teams were positioned. The difference in temperature was marginal both vertically and between the two sides of the measurement. The difference in humidity and temperature between the height of the laser and the height of the camera was insignificant. Fecore concluded that the gradients above the lake did not cause any significant refraction of the laser beam. To reach the maximum precision, Fecore factored in all the possible corrections for the WGS-84 geoid and calculated the mean sea level ellipsoid, the geoid undulation, and the refraction corrections for each measurement. The height of the laser pointer was 1.5 meters and the observation position height was at 1.6 meters. The WGS-84 geoid map shows 0.129 meters geoid undulation at both sides of the measurement. That meant there is no significant difference in geoid undulation. The TLT measurement data shows that at least 2.96 meters of curvature was missing on the total distance of 12 kilometers on the surface of Lake Balaton. There is also a possibility of a local geopotential anomaly, but the WGS undulation map clearly shows that this was not the case.
On the next 4 days of the test, weather made observations impossible. Fog and drizzle reduced our visibility and limited the laser's range. One night, high wind made turbulent air layers and caused a dancing laser beam. This was my first experience at laser observation. When I saw the beam moving so rapidly, I actually said out loud, "What the heck are they doing? Hold it still." No one heard me because their ears were covered and the wind was blowing so hard. I had no idea that wind could cause that optical effect. During the next 2 nights, the temperature dropped to minus 15 degrees Celsius.
I'm going to turn around and show you the ice. The icy lake there.
It eliminated the fog and we were able to see the beam. But the wind chill was down to minus 25 degrees. That really limited the amount of time we could spend outside. Despite the harsh conditions, we were able to achieve our second laser measurement.
On February 26, 2018, on the last night of the team's scheduled stay at the lake, Fecore observed both the blue and green lasers placed at Balaton Fecore and seen from Siofok 12 kilometers away. Measurement 2. On February 26, 2018 at 8 o'clock p.m. The blue laser was placed on the salad at 2.2 meters or 7.2 feet above the surface of the lake at Balaton Fecore. The source of the beam was seen from Siofok 12 kilometers or 7.46 miles away at 1.6 meters above the lake.
Okay, here it comes, here it comes, here it comes.
Here comes the blue. Oh!
I see it. That's a freaking laser pointer, guys.
The reason why I'm on my phone is to show everyone this. That was the 12 kilometers today. So that was. This is worth everything to me.
Yeah.
So
to us.
Mm-hmm. Yes, to us. So I just want to add that I think it's been a brilliant working with these guys, and it's been bloody cold, hard work, and like Karen said, a lot harder than I imagined.
The blue laser was placed at 2.2 meters above the lake surface. By calculating the target hidden height from a distance of 12 kilometers, we get the 3.52 meter minimal observation height to be able to see the ray of the laser beam. The measurement clearly showed that the beam was visible from 1.6 meters above the lake's surface. The ambient conditions at the time of the measurement indicated a marginal refraction of the beam based on the difference of the refractive index on the two sides. Our calculation gave a result of 0.235 millimeter deviation from a perfectly straight line at the time of the measurement.
The corrections have been calculated for the mean sea level, ellipsoid and geoid undulation. Their magnitude is also well within the margin of error.
So after the 12-kilometer observation, we went to the 21-kilometer location, which was in Santad. The lake was super cold, it was completely frozen over, and we couldn't see anything because the wind was just blowing ice into our faces. And none of the 8 or so observers, they could see the laser because of the harsh conditions. That was about all we could do there.
This is my 4th time now, but it always has surprises.
Yeah, well...
And every time it's different. Every time there is a different problem to be solved.
The two measurements performed at Lake Balaton showed that for the 12-kilometer distance, the lake surface did not conform to the WGS-84 geoid model. Lessons from Balaton.
During the measurements taken on Lake Balaton, there were many limitations, especially adverse weather conditions. Although we made 2 successful measurements, all goals set forth were not accomplished in the time frame allowed.
Lasers.
We use different types of lasers, ranging from our high collimated laser to conventional lasers. High collimation is very useful to concentrate the power of the beam to a smaller area, but it's not essential to perform the measurement. The wider beam has the advantage of being easier to locate, but it has the disadvantage of being less bright over long distances.
So let me ask you, how many different types of lasers have you tried?
Several. I think we used about 10 different lasers.
What's the difference between the different lasers that you've used?
Mostly power and collimation.
And can you explain to us a little bit about both of those?
High power lasers are better visible over longer distance, but without the collimation, you will still not be able to see it.
What is collimation?
Collimation is tightening of the beam.
Tightening of the beam?
Yeah.
Okay, so can you explain what that means in actual physical terms?
Yeah, a normal laser diverges over distance in a linear fashion, and a collimated beam reduces that divergence.
So it spreads, essentially?
Yeah.
Okay, so the beam is spreading, and the power issue, which is obvious if you're going to shoot a over a long distance, you think you're going to need a lot of power.
Well, power is distributed over the entire beam. So if you don't have a large amount of collimation, high power is not going to help. The collimation is basically compressing all the power into a smaller beam.
The power of the laser is important, but not the most important part of the technology. Let's make it clear that the manufacturers usually refer to the input power of the device and not the optical output power. There is usually a 1:5 ratio between them, so if you see a laser labeled to 1 watt, that is approximately 0.2 watt optical output power.
Weather. Choosing the perfect weather condition is a key to success with the long-range TLT experiments. Fog is the most obvious factor that affects the visibility of a laser. In thick fog, you may have less than 100 meters visibility. High humidity also decreases the distance of the laser light. Strong winds cause turbulence over the lake and create unstable layers of air with different refractive properties. As those layers are rapidly mixed by the wind, the observer may see the laser beam dancing wildly as if the laser operator was rapidly waving the laser in hand. Timing is everything. Ironically, the conditions Fecore sought manifested less than 48 hours later. Sandor came back to the lake, and this time he was able to walk over the now frozen bay. Salad upgraded with automatic GPS targeting system.
Fecore established at Lake Balaton that targeting the beam to the observation location is the most difficult part of the TLT method. A super-accurate laser aiming device is able to aim the laser in very fine increments. But how would the team know exactly where to point the beam? It was like playing darts blindfolded. The team had to find a solution for locating the target position. Mike came up with a perfect solution and worked to improve the method of aiming the salad. He created software that calculated a bearing change based on 3 GPS locations. With the new GPS update, the salad operator could input coordinates for a new target location, and the laser would point directly to that exact location. There was now a procedure in place to calibrate the actual alignment of the salad first.
This is the actual interface of the device. It's got the settings section here where you actually put in the numbers when you're calibrating your device. And it's got a control section here where you actually control the motors themselves with up, down, and left and right. And then it's got a GPS menu here where you actually have 3 fields that you need to put in. And that's the position of your actual laser where you set it up, your GPS location. And then you have the reference location. That's a location that you need in order for the salad device to know in which direction it's actually pointing the laser beam. And then you have the target location, and that's the maximum distance that you want to shoot your laser at. You fill in those GPS coordinates, and then you press go to target on this device, and it steers the laser to the desired GPS location.
Before any targeting with the laser can occur, the salad needs to be properly set up and calibrated. This process involves careful leveling of all parts of the device and laser. To do this, the salad is put down on a platform, and each of the 4 legs must be adjusted individually to make sure all beams are level. After the device is leveled, the laser beam must also be leveled. This is done in conjunction with a laser level device, which is placed directly behind the laser. The difference in height of the laser level and the laser itself can now be adjusted to be the same across the maximum distance available at that location. Then the setup is ready to start with our newly developed GPS-based terrestrial laser targeting procedure.
The Lake IJssel, Netherlands measurements. After the 2 measurements at Lake Balaton, Fecore performed 5 TLT measurement over Lake IJssel. An interesting feature of the Netherlands is that the lands surrounding the lake are almost all below the level of the lake. On April 7, 2018, at about 7 o'clock p.m., the Fecore team of Mike, Jeroen, and Patrick began setting up the salad on the balcony of a restaurant in Enkhuizen, Netherlands. This was the laser location for all subsequent measurements on Lake IJssel. The setup was completed around 10 o'clock p.m. The laser height was 2.85 meters above the surface of the lake. This location was well known by Mike, who had been there many times over the years. The choice for the reference position was a small stand of trees about 25 meters tall on the opposite shore. Mike had often wondered how it was possible to see the trees over such a great distance. The team chose this location as the Target 1 reference position for calibrating the salad because Mike had been to the trees previously, so he knew the location had good access to the lake for an observation. This was Fecore's first chance to use the new GPS TLT system, so in addition to attempting to measure the lake surface for geoid comparison, the team was also testing this new method. Measurement 3, Lake ISIL Target 1. On April 8, 2018, at 1 o'clock a.m., the blue laser was on the salad at 2.85 meters or 9.35 feet above the lake surface. It was seen at the Target 1 position, 21.26 kilometers or 13.21 miles, at a height of 1.2 meters or 3.94 feet above the lake surface. It took less than 60 seconds for them to see the source of the laser at the Target 1 location.
Can you guys see it?
Yeah, I see it. Yeah, it's there. Okay, yeah, we can see it really well there.
Can you see the reflection on the water?
I'm gonna zoom out. Yes, we do. Yes, we do. Look at that. Wow. Oh, man, that is irrefutable.
Yeah.
Awesome.
Oh, I can watch this all day, you know?
This is awesome.
Yeah, this is really awesome.
Look at that reflection. That reflection absolutely caps it.
Yeah.
Yeah. That caps it. That annihilates any possibility of it being refracted, and that also annihilates any possibility of any convexity.
Yeah.
I mean, you cannot track it with being curved.
The 21.26 kilometer calculations based upon the WGS-84 geoid model resulted in a target hidden height for measurement 3 ISIL Lake, Target 1 location of 18.18 meters or 59.6 feet. The camera height was 1.2 meters. The WGS-84 geoid model differed by 16.98 meters in this measurement, which meant 93% of the target hidden height was visible. The lake temperature was 7.6 degrees Celsius or 45.7 degrees Fahrenheit, and the air temperature was 10.8 degrees Celsius or 46.4 degrees Fahrenheit above the lake. The ambient conditions showed the refractive indexes were about the same on both sides of the lake. TLT calculations factor in any variations in recorded data and geoid datum parameters of the WGS-84 mathematical construct. Both target and laser positions are at 0 meters mean sea level. The WGS-84 geoid undulation map shows a marginal 23 centimeters or 9 inches height difference at the two positions. Measurement 4. After the measurement at Target 1, Mike and Patrick drove 30 minutes to the Target 2 location. Target 2 was selected because it would be within 17.5 degrees panning limit of the salad. Since the salad had been calibrated at Target 1, the automatic GPS system now required only a new coordinate to automatically target that position. This was the first field test of the new GPS TLT software, so it was an exciting moment. On April 8, 2018 at 3 o'clock a.m., the blue laser on the salad was 2.85 meters or 9.35 feet above the lake surface. It was seen at the Target 2 position 28.68 kilometers or 17.82 miles away at a height of 0.85 meters or 2.79 feet above the lake surface.
Okay, check this out, brothers and sisters. 28 kilometers in your face.
Wow. Awesome. That is awesome.
My camera is 85 centimeters above sea level.
Look at that. That's amazing. You can see it reflecting off the lake water.
Yeah.
That's astounding.
That's the nail in the coffin.
Yes, it is.
Oh, this is so great, boss. It's really awesome.
The 28.68 kilometer calculations based upon the WGS-84 geoid model resulted in a target hidden height for measurement 4 ISIL Lake target 2 location of 40.21 meters or 131.9 feet. The WGS-84 mathematical construct differed by 39.36 meters in this measurement, which meant 98% of the target hidden height was visible. 40 kilometers or 25 miles is a very great distance. To perform a 40 kilometer TLT measurement, good atmospheric conditions with great visibility are required. The 40 kilometer measurements were scheduled for April 20th through April 22nd. FE Corps members from the Netherlands, United States, Hungary, and Spain on April 20th in Enkhuizen, Netherlands, for the longest distance laser observation over water in history. The team set up the salad with the blue laser. The reference location was set 18.73 kilometers from the salad at target 3. However, the weather was not in the team's favor. During the first night, the humidity was so high that haze reduced the visibility and dimmed the laser, making any measurement impossible. The second night, April 21st, the humidity was low enough that the team located the laser at the target 3 initial reference location.
We just parked here, and it looks like we're gonna spend the night here. So we're gonna spend the entire night looking for the laser.
They calibrated the GPS TLT system and performed measurement 5 at 12 o'clock a.m. on April 22nd. Measurement 5, Lake ISIL, Target 3. On April 22nd, 2018, at 12 o'clock a.m., the blue laser was on the salad at 2.92 meters, or 9.58 feet, above the lake surface. It was seen at the target 3 position 18.73 kilometers, or 11.64 miles, away at a height of 1.6 meters, or 5.25 feet, above the lake surface. The 18.73 kilometer calculation based upon the WGS-84 geoid model results in a target hidden height for measurement 5 ISIL Lake target 3 location of 12.504 meters or 41.024 feet. For measurement 5, the WGS-84 mathematical construct differed by 10.904 meters, which meant 85% of the target hidden height was visible. FE Corps examined the effects of refraction through the gradients in the air by adjusting the beam vertically. It was concluded that with the present ambient conditions at measurement 5, the beam was refracted downward by a maximum of 1/100th of a millimeter. Measurement 6. The team moved to the 40 kilometer location, or target 4. At 40 kilometers, finding the source of a laser beam with the naked eye is almost impossible, especially if there are other light sources on the horizon. A telescopic camera was the solution to distinguish the laser from the other lights. Measurement 6, Lake ISIL, target 4. On April 22, 2018, at 2:19 a.m., the blue laser was on the salad at a height of 2.92 meters, or 9.58 feet, above the lake surface. It was seen from the target 4 position 40.14 kilometers, or 24.94 miles away, at a height of 1.5 meters, or 4.92 feet, above the lake surface. The 40.14 kilometer calculations based upon the WGS-84 geoid model resulted in a target hidden height of 90.81 meters, or 297.33 feet, for measurement 6 Lake ISIL target 4 location. The WGS-84 mathematical construct differed by 89.31 meters in this measurement, which meant 98% of the target hidden height was visible.
Yesterday we had a little bit of bad luck because the beam of the light was not so good visible with the camera. We could definitely see it with the naked eye, but to catch it on camera it was really difficult. So we have adjusted some things for today, and we are truly expecting better results.
Yeah, but the intensity is going down.
Yeah, it's going way down.
Okay, just put it one step up, Sandra. Okay, one more. Put the steps.
Wow!
Put the steps on.
I think I just caught that.
250,000. One more.
Almost see the scenes.
One more. Okay. Yeah, one more. That's
Maybe
it,
one more. Maybe. Oh, yes,
yeah,
I can
one
see
more.
it.
One more.
One more.
You got it?
I could tell. I was looking right at the beam. Or down.
Down?
Yeah.
It's going up.
Get one now. See what's up.
Yeah, just now. I think we're looking at it.
Yeah.
With the naked eye.
FE Core examined the effects of refraction through the gradients in the air by adjusting the beam vertically. It was concluded that with the present ambient conditions at measurement 6, the beam was refracted downward by a maximum of 0.064 millimeters.
We were shooting the laser 40 kilometers across the lake. We did find it on the target location, but it was already getting light, so the intensity of the beam was almost not visible anymore. And we had some issues with finding the right orientation of the beam itself. So now that we know where to actually point it, we're going to try it again today to get it on tape.
Measurement 7. In the evening of April 22nd, the team returned to the Target 4 location. They worked late into the night taking many pictures. Rick's camera was set to take one picture every 5 seconds.
So the source of light, whatever's going on top of the water, you're not going to be able to see it. There's too much humidity. The water's blowing, it's spraying.
Yeah, and it's windy on your side, right?
Oh, it's real windy on our side.
Yeah. Okay, buddy.
Patrick, can you see it then? So, there we go.
Nothing at all?
I cannot take it off camera. There's just not enough light coming off from it.
First of all, there's too much light pollution coming at us too close. Then it'll knock that out.
Measurement 7, Lake Isle, Target 4. On April 22nd, 2018, at 11:20 p.m., the blue laser was on the salad at 2.92 meters or 9.58 feet above the lake surface. It was seen at the Target 4 position 40.14 kilometers or 24.94 miles away at a height of 1.5 meters or 4.92 feet above the lake surface. The parameters and outcome of measurement 7 was the same as the one from the previous night. The only difference was the maximum refraction of 0.133 millimeters caused by the slightly different ambient conditions. The observers should not have seen the laser at any height below 89.3 meters or 293 feet, but the beam was recorded from a height of 1.5 meters or 4.92 feet.
Stop. Okay. Bring it down now. The laser down.
Going down.
Zach, if you want to record some of this, you can. I didn't know what you were doing.
I'm trying to record something. At least.
Okay, you still coming down? Yep. Okay, stop. Go back up a little bit.
Conclusions.
The results of the 7 TLT measurements indicate that these two lakes do not conform with the WGS-84 mathematical construct and that they lack the predicted convexity. The testing results agree with the analysis of error sources. In summary, the testing results of the lake surfaces were plus or minus 0.2 meters and the relative accuracy was within 1%. In conclusion, the TLT measurements met the accuracy of the experiment design requirements, and provided a definite deliverable output.
The surfaces of Lake Balaton and Lake IJssel do not conform with the predicted convex shape of the WGS-84 mathematical construct. Through analyzing error source models of TRT measurements and corrections for the geoid surfaces, we determined that the TRT measurement results conclusively prove our hypothesis of non-convex water surfaces.
Never in history have independent researchers been capable of falsifying these axioms by direct observation and measurement. Fecore has made new and meaningful discoveries with its very first project establishing an enormous amount of missing predicted convexity on both lakes. Thanks to the support of all Fecore subscribers and project participants, a great addition to the body of scientific knowledge has been made.
We welcome you to join Fecore by becoming a member and supporting our scientific endeavors, or even contribute in your field of expertise. You are invited to follow our team across the earth as we continue to explore the true nature of our world.